This presentation looks at the topic of gravity. There are two parts to this really. The first is the everyday experience we've all had, which is just that stuff falls. The second looks at larger scale motions such as the orbits of satellites around the Earth or indeed planets around stars. The main teaching point here is that the work of Isaac Newton was to identify that these two things could be explained by the same common branch of physics. One single equation does both. Before looking at Newton's role though, let's have a look at the background. What was the sort of thinking like before him? How is the story? Well, it really begins in ancient Greece with Aristotle's work. He formalized the expectations of the time, and it's largely the intuitive understanding that most people would default to if they don't get physics lessons. He argued that as more massive objects are clearly heavier, there is clearly a greater pull pulling them towards the Earth, and therefore he expected them to accelerate towards the ground at a higher rate compared to less massive objects. He was also credited for suggesting that in order for things to move, you have to continually apply a force to them. In the everyday experience, if you shove a book across a desk, it comes to a stop. Aristotle therefore argued that unless there's a force continually moving things forward, things naturally stop. It turns out, while Aristotle had many good ideas, these weren't the best, and because he never really tested them in the more modern sense, well, it was a bit of a problem. A long time later though, in the sort of 15 to 1600s, Galileo started challenging some of these ideas. You see, he suggested that in fact things might fall at the same rate. Also, that the natural behavior of objects was to keep going at the same speed. He said that slowing down only happens when there's friction. Famously, Galileo is described as having demonstrated this quite publicly by dropping a very dense steel cannonball and a much less dense brass cannonball off of the Leaning Tower of Pisa, which is quite a tall building at the time. You see, the reason most people can't see that objects fall at the same rate is because of two small problems. The first is that air resistance really can sometimes have a big impact. If you drop something like a piece of polystyrene versus a book, well, the piece of polystyrene will take clearly far longer to hit the ground. It's not because their natural acceleration is different though. It's because the air resistance is going to have a far greater effect on the less dense objects such as the polystyrene. If you drop two very different masses but both at least a certain density, then the effect that Galileo describes works really well. That's why he chose brass and steel. His second problem was that the time involved for dropping things is really quite small. If you drop something from the ceiling, for example, it will take less than half a second to hit the ground. In his time period, timing devices really weren't that great. And even if you did have the best timing tools, you'd still have a problem because it's very hard to release things at exactly the same time. Galileo's work was based around slopes instead of dropping things vertically. He argued that this is essentially the same process, just that you've slowed it down. It only really works though if you have very low friction slopes, and one of the things he was able to work on was to find ways to make sure the friction was kept to an absolute minimum. There are quite a few ideas he came up with. The first observation is that if you have your starting ramp here and you let a ball go from the top and roll it down, well, it doesn't matter what ball you use. If you use a low mass or a high mass ball, they will end up at roughly the same height at the end. Also, he identified that no matter what you do, as long as you're letting it go and not pushing it, the final height over at the other side of the ball is never going to be greater than the starting height. Using a pair of ramps that were identical, he was also able to show that the process is symmetric. That means that the only thing that matters in terms of working out the speed is the height of the object. In our modern times, what we'd say is that the height determines how much gravitational potential energy is left. So this ball here, for example, has fallen this much, therefore it's lost a certain gravitational potential energy, and thus gained a certain kinetic energy, and therefore that height corresponds to a particular speed. The same speed would be true over there if there's no air resistance friction. Galileo then sort of played with the angles. By having a shallower and shallower angle, you would have a greater amount of time to measure the ball going up. He identified that the key thing here is the vertical displacement and not the displacement parallel to the ramp. You see, he would say these are all at the same distances because he's talking about the distance from the ground, not the distance along the ramp that might have confused the likes of Aristotle. Because he was able to get very good data, he was able to identify an interesting pattern. You see, the rate of deceleration as you roll up here is quite high. As you roll up there is quite low, and as you roll up here is really quite low indeed. He started asking the question is, well, what would happen if you keep reducing the shallowness of this ramp more and more and more until eventually it's flat? And the conclusion of his pattern was that in that case, with no friction along there, the ball should keep going with no acceleration at all. That is essentially Newton's first law of motion. The second piece of work that Newton drew upon was the work of Kepler. Kepler was an astronomer and he benefited from a very large collection of measurements of planets going around our sun, going back probably over 100 years. Kepler was able to do the brute force data analysis. He tried to test all the different patterns that he might find, and he came up with 3 mathematical laws, one of which is depicted in this picture. You see, most orbits are not circles, as you might assume. They're in fact ellipses, a sort of squash circle. And the sun is not at the center either. It's sort of off to one side. Now, this picture is an exaggeration, but you get the idea. One of Kepler's rules was that if you have this type of motion, then when the planet is in this position, it moves relatively slowly. But when the planet is much closer, it moves a lot faster. And Kepler was able to identify that the area of this angle that's swept out, this sort of segment, is always consistent. So in 1 month, the planet might travel this much. Later on in the year, another month, it'll travel a further distance around the circle, ellipse, but these areas tend to be about the same. For Newton, the key point here was that the speed of the planet is changing based on how close it is to the sun. Therefore, when you're closer, there is a greater force. And he realized that the sun must be producing that force, or rather the sun and planet combined do. And that led him to conclude a certain thing. The main stroke of genius, really, the reason this became such a famous example, is because both Galileo's and Kepler's work were already very well established. These were really interesting ideas that we really believed as a community in that time period. Newton was able to then provide a missing ingredient, shown by this equation here, and when you apply that equation to both of the previous examples, it explains them. He found the underlying explanation behind patterns that other respectable scientists had come up with. That's a very good thing in physics. That's what we're really interested in, and it happens quite often. Newton's law of universal gravity says that the force between any two masses, absolutely any two, no matter where they are, what they are, so on, just depends upon the mass of each of them, m1 and m2, and the separation, the distance here marked as a radius. But it's squared, and it's on the bottom. This isn't inverse. What this means is if you're twice as far away, you're not going to have half the force between you, but you're going to have a quarter of the force. This is known as an inverse square law. There's quite a few of them in physics. It's really a property of three-dimensional space rather than the actual things it encounters, but it's quite recognizable. Now, saying the pattern that force depends upon the masses and the separation, well, that's all well and good, but in physics we want more than just a rough pattern. We want to know how big that force is. So based on our units, we ask the question, Well, if I have a 1 kilogram and another 1 kilogram 1 meter apart, how big would that force be? And that basically is this number capital G called the universal gravitational constant. It turns out it is super teeny little tiny, times 10 to the power of minus 11. So the force between 2 kilograms sitting a meter apart is basically so small you're never going to be able to measure it. For that reason, you don't notice when someone walks past you. It would be quite awkward if you got too close and someone sort of grabbed onto you like a magnet. It's also true that you don't notice the effect of the moon in the sky. You see, the moon can pull the tides preferentially to one side of the Earth, but we don't feel heavier when the moon's underneath and lighter when the moon's above us. Again, that would be quite inconvenient for our lives. But we can work out the size of those effects. In fact, at our scale, the only thing that's big enough, and the only thing that can be big enough in this equation to ever overcome this tiny little number is the mass of a great big honking planet. And that's why you only really notice the effect of Earth's gravity. It should be pointed out that the force is symmetrical between both objects. People say that the Sun pulls the Earth into an orbit, but technically the Earth also pulls on the Sun, and the two of them, we say, together orbit a common central point. Usually though, Earth's so small compared to Sun that it really doesn't make much difference, and the centre of the system is actually inside the Sun itself, but this can become insignificant for cases where the two bodies are similar. For example, two asteroids orbiting around each other, or two stars going around each other, or a moon going around a planet, that kind of thing. This equation is also a little bit testable. You see, even though it's hard to measure everything, if you plug in the values that we've later learned, such as the mass of the Earth and the radius of the Earth, and replace m2 with just m, well, you can process these numbers. And all these numbers together, when you do the sum, turn out to be about 9.8. This is the value we normally know as little g. This was W equals mg from the early years of physics. This is only true for the surface of the Earth. It doesn't apply if you're underneath the ground. It doesn't apply if you're up in the air. And it does actually vary a little bit depending upon what's underneath you. More importantly for us as physicists and as a species, this value depends very much on where you are in the universe. So by using this equation here, along with measurements of, say, the size of the moon, scientists were able to work out how strong the gravity would be on the surface of the moon, which then allowed them to figure out how you could, at least roughly, be safe when you're trying to land and make sure you've got enough force to lift off at the end. This is quite handy. It also allows you to understand why we can't, for example, go and visit Jupiter. The strength of the gravity would be so big that basically it wouldn't be possible for us to walk around. This video link here takes you to a lovely YouTube video where they're going to take you through about 6 or 7 different worked examples. They deal with things like converting units, doing the algebra, all that kind of stuff. If you have any doubt at all, watch this video. That will explain everything you need. For you to practice with, I've given you this set of 6 equations. Notice that the first one is a state question. That's just asking you to tell us what the rule is. You can use words, but you'll find it tricky. The best approach is to write an equation. The second one is a show that question. That means it's given you the answer and you've to put on your best working to prove that is the case. Make sure you have every step in place. The next 3 basically ask you to take the standard equation, plug in the numbers and work it out. They're a bit tricky though because the powers can be quite small in the case of an atom or really quite big in terms of planets going around stars. Final question asks you to work out the separation between 2 particles. Please note for all of these you should ensure that your final answer has the correct number of significant figures. The rule we use to work out how precise we can claim our data to be is, well, we have to match it to the data we're using. For example, here there are 3 sig figs, so is there. Back to Galileo's claim. You see, Galileo said that all objects ought to fall towards Earth at approximately the same speed as long as air resistance can be ignored. Newton's work allows us to go a little bit deeper into that. First of all, we know from either this equation, the new one, or the old one, that the force on an object is going to be directly proportional to its mass. A 1 kilogram object will have a force on it of approximately 9.8 newtons. If you compare it to an object twice as massive, well, the bigger one will have double the force as well. So Aristotle was right. More massive objects do indeed experience a bigger force acting on them due to gravity. But the bit he was wrong about is that doesn't mean they accelerate towards the Earth faster. You see, Newton's second law, this one here, corrects that problem. You see, it says that in order to get a certain rate of acceleration, well, the amount of force you need depends upon the mass. In other words, the object that's twice as heavy will require twice as much force to do the same as the lighter object. These two effects exactly cancel out, always. It doesn't matter how big you are, you're going to fall at the same pace as something much smaller, as long as you can ignore air resistance. This is the more formalized working. We're saying that acceleration is unbalanced force over mass, substituting in what the unbalanced force would be in the case of free fall, which is just this equation here, W equals mg. Mass cancels with mass, and then you end up with a rather simple equation saying the rate of acceleration for absolutely any object only depends upon the strength of the gravity on your location. Some people say that physicists are making up stories here. Notice we're perfectly well aware that if air resistance is a significant factor, this isn't really true. This slide shows an extract of one of my favourite physics teachers, a guy who has a website called Flipping Physics. And not only does he offer lots and lots of lessons that I recommend, he also takes the time to make quite a lot of very high quality content of demonstrations. In this case, he's doing an experiment that I would normally show in class and that you can even attempt to do at home as well. He has 4 different video clips here and he's dropping an object from 2 meters high in his garage. Notice this is actually quite difficult. To hold a book out at arm's length at a certain height and let it go at the same time can be tricky. Doing all that on top of a ladder, well, it can be a little bit dangerous. Doing all of that while making sure you're in the camera shot can also be a bit of an issue. But the point is, it doesn't require any sophisticated or fancy equipment. You might ask though, why don't we do it just from 1 meter? Well, the problem is it takes less than 1/10 of a second for the book to drop that distance. So you really don't have much to go on. If you make a small mistake with the release point, then that's all you see at the bottom. Secondly, you might ask, well, why is he using books? So you see, well, books are not great because you notice this one's rotating. That's because it has a rectangular shape. But they do have one advantage. They're dense enough that the air resistance at these speeds will be close to negligible. But they're also not going to be so dense that they're going to start chipping the ground or become dangerous if it lands on a toe. It's a sort of nice middle ground. There's a lot of that in all science. If you want to clearly show the effect, you have to choose the variables that you're working with so that they actually allow you to clearly see it. If you tried this going up 50 meters, well, you're not going to be able to do that. And you'll probably be able to mess up the landing zone. There's a bit of compromise. Speaking of doing this over greater distances, the Brainiac TV show decided they were going to take this effect and do some testing themselves. I think this is a fantastic clip that takes you through the whole story again and basically gives you a step-by-step demonstration. You can see in the image that they are lifting a cooker and a pillow up quite high in a car park. They're using an industrial crane, which I think is about 50 meters tall. That's about the same size as the Leaning Tower of Pisa. In these cases, the objects will have enough time to get fast enough for the air resistance to start affecting some of them. And this way they can do tests to show when this effect is true, i.e. when the resistance is small, and when it isn't. It's a lovely video. The other approach for demonstrating this all really works is to do the experiment in a vacuum. You see, that's when we're claiming it's relevant, but it can be quite tricky to do. We're not going to do this in a classroom. You're probably not even going to get this at university. It's just too darn expensive to have big vacuum chambers. But if, say, you happen to be going to the moon in the 60s, well, it doesn't cost you much to take a hammer and a feather along with you. And that's what this video clip is showing. This astronaut is dropping the two of them on the surface of the moon. This little video clip has been viewed by virtually everyone who studies science all around the world. You can have a look for yourself. Fair warning though, it was shot in the 1960s on the surface of the moon, so the video quality might not be quite as good as you're used to. The second video clip over here shows an experiment presented by Brian Cox. Over in America, one of the old sort of missile silos they had during the Cold War has been converted into an outer space testing chamber. So they have this very, very tall building which is very, very strong, and they've basically set it up so they can pump out all of the air inside to recreate some of the conditions of space to test out things like the space shuttles. Well, Brian Cox and his team went along and they rigged up a pair of electromagnets, and they've hung on it a bowling ball and a very large feather. They drop them about 40 meters or so, and they are looking to see how the gravity affects each of them. So they do it first of all with the air there, and surprise, surprise, the bowling ball lands much faster or much sooner. And then they suck out all of the air and repeat the experiment. It's a very nice result, and I encourage you to click on that link and have a look as well. Moving on to the one case where you do have to deal with air resistance is the case of terminal velocity. You see, normally we don't talk about the effects of air resistance because it's just, frankly, too darn difficult. Even at university physics, you can go through an entire degree and never really touch on the effects of air resistance. It's just really quite difficult to deal with. Even if you did understand the equations behind it, it depends very much on the particular speed and shape of the object, and you pretty much end up having to use computers to process the sums. But in one particular case, that's the case of terminal velocity, we do know exactly how big the forces are. Because terminal velocity is when the downward force pulling you down, your weight, is exactly balanced out by the force pushing you back up. That's the air resistance. You see, if you jump out of a plane, well, you're going to go faster, and then faster, and then faster, and faster, and faster, and faster, and faster. At some point, you're going to be going so fast that you're going to have to push an absolutely crazy amount of air out of your way every second, and that's going to take quite a big force. Think of sticking your hand out of the car window when you're going really fast, but much, much worse. Should maybe tell you that if you do go skydiving, it's quite common for people to be sick immediately upon landing the first time. Their bodies are really shooken up and beaten by those forces acting them all the way down. That's what makes it so exciting. We'll come back to that though. This video clip here shows a science experiment when you're looking at measuring the terminal velocity of a ping pong ball. Rather than dropping a ball through a huge amount of air and waiting for it to speed up, they use a fan in the base of this tunnel. They blow the air faster and faster and faster until the ball hovers just right in the middle. You see, if the air is too slow, the ball will fall. If the air is too fast, the ball will move up the tube. By adjusting it until it sits just right, they can work out what the terminal velocity of that object is. This is something that's routinely done at universities. The final video clip here shows you some real skydivers. This is quite an interesting one. A bunch of friends jump out of some planes because why not? Bit of fun. But then someone is hit. I'm not sure. Some say he was struck by a meteor. Some say he was hit by another skydiver. But either way, one of the divers gets knocked unconscious. Now, he turns out he's fine. Don't worry about him. But it does allow us to see what happens to the human body if you're not in control of it. You see, normally when people are filming skydivers, they're very good and careful, skilled people, like this person. But if you're unconscious, you cannot just ragdoll your way down through the air. As a result of that, the people with this person noticed something was wrong, came down to them, got a hold of their parachute cord, pulled it, and this person landed safely. You might ask, how are they able to maneuver? How are they able to catch this person up if everyone falls at the same rate? Well, you see, that's where it gets interesting. By changing the shape of your body and your aerodynamics, you're able to increase or decrease your terminal velocity. You're also able to maneuver from side to side. This video clip ties in nicely with the following slide. If you should jump out of a perfectly good plane, well, very quickly you'll start speeding up. And roughly 1 second later, you'll be going 10 meters a second. That's sprinting as fast as you can. 2 or 3 seconds later, well, you're already going to be going the speed of cars. If you wait something like 1 minute, well, you're almost certainly going to have achieved your terminal velocity. And that's a very high speed indeed. You see, as you go faster and faster and faster, the air resistance not only increases, but it increases at a faster rate, which means your acceleration rate, the gradient of this line, curves off really quite quickly. To go a little bit faster now, well, that'd be quite difficult. Once you're at your top speed, your terminal velocity, you'll stay there. I mean, technically, if you look at people that do the sort of world record attempts, they try and do it from the edge of space. That's because the air is less dense there, so they can get a slightly higher terminal velocity. But I don't really want to talk about that too much. But there's a relatively long period here where the speed is roughly flat. That's because the weight pulling you down is being exactly matched by the air pushing back up on you that you're trying to force out of the way. As you approach the ground, doesn't take long by the way, just a couple of minutes, you might realize that you don't want to hit the ground at that speed. So you pull your parachute and you have a far larger surface area. That means you're going too fast basically. Your speed multiplied by your surface area tells you how big the force is going to be, and since the area has just increased, well, the force pushing you up is far higher than your weight. So you decelerate really fast. One thing to note though is when you see this on a video clip, it looks like the person shoots up the way. That's not the case. The reason it appears to be that they're shooting up the way is the person who's filming is still free falling. It really wouldn't make much sense if a parachute made you move up the way, because, well, then you would never land. And what does happen is your parachute means you end up with a different terminal velocity. In this case, it's been described as 8 meters per second. Now that's still a good running pace. That's a run across a classroom every second. But if you land carefully like that, you have a fighting chance of doing it without breaking your legs and things. You probably don't want to land on the side of a cliff though. This final little line shows the impact of the ground. As soon as your legs hit the ground, well, one way or another, you're going to stop quite quickly. This slide here is intended to provide a bit of bonus knowledge to those curious folks that really want to look a little bit more at the actual values of air resistance and how it depends upon the cross-sectional area, a little bit about the sort of smoothness of the shape, the density of the fluid you're going through, and the speed. It's a square term here. It's actually a bit more complicated though, because there's this other factor that comes into it as well, and I don't really want to go further than that. Feel free to have a look at the Wikipedia article and some of the YouTube videos, but I'll tell you now, this is a very complicated thing for anyone to understand, even if you have a physics degree. But there is quite a lot of work involved here. This is the sort of engineering that comes into designing faster fighter